Welcome to lesson number 7 of the NumPy crash course. Previously, we looked at how we can manipulate array shapes by flattening, flipping it over its diagonal, resizing, as well as a few other functions. In this lesson, we'll continue learning more about functions that are often used to manipulate arrays. We'll begin this lesson by learning how to horizontally stack two arrays. We'll begin using the hstack function, which stacks arrays in a horizontal, column-wise sequence. We'll start off by importing NumPy as NP, set x, sum array x equal to np.arrange 4. We'll have 4 elements from 0 to 3, reshaped.reshape 2 and 2 into 2 rows and 2 columns. Printing x, we get a 2 by 2 array. On a different cell, we'll make another 2 by 2 array. Set y is equal to np.arrange 4, 8. We'll have 4 elements from 4 to 7, also reshaped into 2 by 2 rows and columns. Print y. And now, with the hstack function, we can horizontally stack these two arrays. Set z is equal to hstack. The parameter consists of a tuple of arrays. The arrays will be x and y, and don't forget to use the np alias before calling hstack to access the function itself. Note that for this to work, the arrays must have the same shape along all but the second axis. Outputting z, printing it, displays the two arrays stacked along one another. The arrays being stacked horizontally must have the same shape as we previously said along all but the second axis, which runs horizontally across the columns. The first axis, which must be the same, runs vertically downwards across the rows. They must match for both arrays. One thing to note about horizontal stacking is that it concatenates along the second dimension. If you print the shape of the initial array, we'll print x.shape. The output is 2, 2. Although printing the shape of the stacked array, print z.shape, will output 2 and 4. Clearly, concatenation occurred along the second dimension, increasing the number of columns. If I change one of my rows to be 1 and the number of columns to be 4, this would still work. However, an exception should be thrown here, since they do not have the same shape along the first axis. Recall that for horizontal stacking, along the first axis, the shape must be the same. Suppose instead we had an array with 8 elements ranging from 0 to 7, which can be reshaped as a 2 by 4. We would still be able to horizontally stack x and y, since they have the same shape along the first axis, as you can see. Whereas if I change this to a 4 by 2, the dimensions will not be compatible. However, if we were to vertically stack these two arrays and stack them along the first axis, it would work just fine. When vertically stacking, unlike horizontal stacking, the arrays must have the same shape along all but the first axis. X and Y have the same shape along the second axis, which runs horizontally across the columns. Therefore, we'll vertically stack them along the first axis with np.vstack. This also takes in a tuple of x and y, print the result, and it stacks them vertically. One thing to note about vertical stacking is that unlike horizontal stacking, it concatenates along the first dimension. If you print the shape of the initial array, as we did previously, the output is 2 and 2, although printing the shape of the stacked array will output 6 and 2. Clearly, concatenation occurred along the first dimension this time, increasing the number of rows. The equivalent to stacking is concatenating. We can achieve the same results as stacking by concatenating two arrays and specifying the axis along which we want to concatenate them. Recall that vertical stacking joins the two arrays along the first axis. The first axis is denoted by the index 0. So what we'll do is we'll np.concatenate. Again, this takes in a tuple of arrays, x and y, and we'll concatenate them along the first axis. Axis is equal to 0. If we set this equal to a variable w and print w, clearly concatenation along axis is equal to 0 has the same effect as vertical stacking. If we wanted to achieve the same result as horizontal stacking, recall that horizontal stacking occurs along the second axis, which is denoted by index 1. If you try to run this, an exception is thrown since they do not have the same shape along the first axis as would be needed for horizontal stacking. We can fix this by changing this back to a 2x4, and concatenation should work just fine. To show that horizontal stacking and concatenation along the second axis are the same, we'll also horizontally stack these two arrays. We'll set z is equal to, we'll reuse z, we'll set that equal to np.hstack x and y. What we can do now is we can use the comparison operator equal to check if both of these arrays are equal. So we'll do z is equal to w and we'll print the result of that. What we get is it returns an array that displays true for every element, indicating that these two arrays, z and w, are identical for all elements. Therefore, concatenation along axis is equal to 1, and horizontal stacking are indeed equivalent. This also introduces the concept of comparing two arrays with the equal comparison operator. The same concept would apply to vertical stacking if you were to concatenate along the first axis, but we're not going to do that since that would throw an error. That is all for horizontal and vertical stacking. Next, we'll cover depth stacking. Depth stacking is not as intuitive as horizontal or vertical stacking, which stacks along the third axis, the depth axis. Before proceeding with depth stacking, let's ensure that both arrays have equivalent rows and columns. We'll therefore just set y is equal to x times 2, multiplying all of its elements by 2. Both arrays now have 2 rows and 2 columns. We'll declare depth stack is equal to numpy.dstack, which takes in a tuple of arrays, x and y. Since both of these arrays are two-dimensional, and due to the fact that depth stacking stacks along the third dimension, which we don't have, what it will do is it will first reshape both of these arrays by inserting a third dimension of size 1. If we go back to our building analogy, both arrays would now have 2 floors, each floor with 2 rooms, organized in 2 rows and 1 column. If we print depth stack, since we added a third dimension to our array, stacking occurs along the third dimension, such that the third dimension previously added now contains 2 columns per floor. We can show this by printing depth stack dot shape, which results in a shape of 2 floors, 2 rows, and 2 columns. Main thing to note is that dstack adds an extra dimension 1 for both arrays. Unlike vertical and horizontal stacking, it concatenates along the third dimension, increasing the number of columns from 1 to 2. To show that the dstack function adds an extra dimension, we can explicitly declare that dimension ourselves for both x and y. Both of these will now have a shape of 2, 2, and 1. Depthwise stacking would then occur along the third axis, joining both array columns and resulting in a shape of 2 floors, 2 rows, and 2 columns. Similar result to what we encountered previously. Do note that both arrays here have a third dimension of 1, and our array here has a third dimension of 2. So clearly depth stacking occurs along the third dimension, increasing our number of columns by 1 per floor. Next comes column stacking. This is another case where the name gives away the functionality. We'll revert these back to being 2 by 2 arrays. We will get rid of the third dimension. And what column stacking will do is it will simply stack both of these arrays along the second axis, which runs horizontally along the columns. In this case, it is equivalent to horizontal stacking along the columns. So we'll call np.columnStack, also taking in a tuple of arrays x and y, and by outputting the result, print, it horizontally stacks both of them in a column-wise direction. We can actually check if this is equivalent to horizontal stacking with the comparison operator, and we will compare it to a horizontal stack, np.hstack, taking in a tuple of x and y. The result is an array that returns true for every comparison between each respective element that composes both the horizontal and column-wise stack arrays. Column stacking and horizontal stacking differ when dealing with one-dimensional arrays. If we revert x and y to be one-dimensional by taking off the reshaping, with horizontal stacking, if I were to just print this on a separate cell and get rid of this, print hstack, horizontal stacking for a one-dimensional array, it would line both arrays up along the second axis, whereas column stacking would still stack them up as columns to make a two-dimensional array. In this case, the resulting output with 1D arrays from these two functions is not equivalent. The same concept applies to row stacking. The name speaks for itself. We will revert these back to being 2 by 2 arrays, putting back the reshaping. What row stacking will do is simply stack both of these arrays along the first axis, which runs vertically along the row. In this case, it is equivalent to vertical stacking. We'll call np.rowStack, also taking in a tuple of arrays, x and y, and if we print the result, it vertically stacks both of them in a row-wise direction. We can also check if this is equivalent to vertical stacking with the comparison operator. Set it equal, and we'll compare it to a vertical stack, vstack, taking in a tuple of x and y. The result is an array that returns true for every comparison between each respective element that composes both the vertical and the row-directed stack. In this lesson, we learned 5 different ways that we can stack arrays, either horizontally, vertically, depth-wise, column-wise, and along rows.